Welcome to qnawire.
We're given that we have two particles, one of mass 3m and one of mass m, that are meter apart, and we want to know where can we put a third mass, capital M, so that the total force on it from these two masses, the total gravitational force, will be 0. So really the mass of this third particle doesn't matter. If that particle is stable, then any particle would be stable at this point. But so we want to know where we can put it, and right away we can see that it's going to have to be somewhere between these two particles. If we put it over here on the right, then both of these other particles will be pulling it to the left, and if we put it over here on the left, both particles will be pulling it to the right. So the only place where it can possibly be stable is in the middle, where the mass 3m will be pulling it to the left, and mass m would be pulling it to the right. So I'm going to say that it's somewhere here, and we want to find where this is. So that's a capital M there. And I'll define this position then as x. So now we can write out our force equations, and then we should be able to figure out what this value x actually has to be. So because we want this to be in equilibrium, we can say the net force on x, on particle x, needs to be 0. And so there's two forces acting. There's the force of particle 3m on it. So that will be pulling it to the left. So that'll be a negative force. So we have negative g, and then times the two masses, 3m times capital M, and then divided by the distance, which, as we've defined our coordinates here, is just going to be x squared. And then pulling the other direction to the right, we have, again, capital G, and then times little m, times capital M. And now our distance between this mass I've labeled 2, the single m, and capital M, if the total distance here is 1 meter, then the distance between these two will be 1 minus x. So we have 1 minus x squared. And so because we know that this has to equal 0, we can solve for this now. So we can actually cancel out these little m's, these big M's, and these G's. So we're effectively just dividing by those on this side of the equation. And we divide 0 by that, nothing happens. So we can just get rid of those. So those don't affect the answer at all. Any value you want to plug in for M, we'll get the same position that this capital M mass needs to be in to be in equilibrium. So we're left then just with negative 3 over x squared plus 1 over 1 minus x squared. And so this whole thing needs to equal 0 since we have no net force there. So our only unknown is x, and so we can solve for that, and we should get that x equals 1 over 1 plus 1 over root 3, and that should come out to be 0.634. There's actually going to be two solutions to the equation for x here when we solve it. One of them will be negative, and we need to discard that solution. So because of how we've set up our coordinate system here, we've kind of implicitly said that this capital M particle is somewhere between these two. So that's built into how we've written our force equations here. Because we've set up this distance as 1 minus x, that means we're kind of saying it has to be something in this range here. So mathematically it works that there'll be a position somewhere over on the left where this particle will be in equilibrium, but that's only because our equation doesn't actually work out there. So physically there's only going to be one solution. And so this is just sort of an artifact of how we've set up our system here. So we get that at 0.634 meters. And so that's our answer. So it's a little bit closer then to the smaller particle than to the bigger particle. So that makes sense. It needs to be closer to the smaller one since this is going to have a smaller gravitational force at a given distance than the larger particle. So then in the next part, we're asked to evaluate or talk about the equilibrium condition itself. So we know that when we put this particle at this position, there'll be no net force on it. But is this a stable equilibrium? And so just kind of intuitively, we can probably see that first along the x-axis where they ask us to think about it, it's not going to be stable. So if this particle were to move just a little bit to the right, then the force that this particle, particle 2, lowercase m, applies on it is going to be larger, and the force that particle 1 of mass 3m applies on it is going to be smaller. So if it moves just a little bit to the right, it's going to want to keep moving more and more to the right. And this opposite case will happen if it's moving to the left. So this is an unstable equilibrium in the x direction. So in the x direction, we say this is an unstable equilibrium. And then they also ask us to think about in the y direction. So if it moves a little bit up or a little bit down, is that going to be stable? And so in this case, if it moves just a little bit up, well, both of these two other particles are going to start pulling it back down a little bit. It's attracted to both of them. It's now above them vertically, so it gets pulled back down. As it gets pulled back down to being parallel with them again, then that force will go to 0. And just the opposite happens if we're pulled downwards a little bit, it's going to be pulled back up. So in that case, whenever it leaves this equilibrium position, it's forced back to where it was. So in the y direction then, it's a stable equilibrium. If we had to pick though, is it stable or unstable, we would say that it is unstable because it's unstable in just one direction. That means any kind of small perturbation or movement to it will make it leave this equilibrium position.